Arnold Ross, a mathematician and educator in the late 1900s, suggested that we think deeply of simple things. He founded the Ross program with this motto. So here's a simple thought. What are the following sums? 1, 1 plus 2, 1 plus 2 plus 3, and so on. When I was young, I used to arrange pennies in triangular arrays like these, so the sums listed count the number of pennies involved. In general, the simple question is what is the sum of the first n positive integers, 1 plus 2 plus 3, and so on, up to n. In the event that you haven't seen the famous sum formula, pause the video and have a think about it. If you have seen this, you probably know that you can compute the sum of the first n positive integers using the formula n times n plus 1 over 2. This is one of my favorite formulas, because if we follow Ross's philosophy and think deeply about the formula, we can gain exposure to many areas of mathematics. If you've seen this formula before, it is highly likely that its truth was guaranteed using proof by induction. To prove the theorem by induction, you verify that the statement holds for the base case when n equals 1. Here we check that 1 equals 1 times 1 plus 1, all divided by 2. Next, we assume that the formula holds for some given fixed integer n. And then, we use this assumption to prove that the formula holds for the next integer, n plus 1. We can see that the sum of the first n plus 1 integers is given by the sum of the first n integers plus the extra term n plus 1. Applying our formula induction assumption, we then have a single fraction addition to compute. Obtaining the common denominator, we can add the fractions and then factor out the common n plus 1, showing that the sum of the first n plus 1 integers is in fact n plus 1 times n plus 1 plus 1, all divided by 2 is required. The result then follows by induction. Proof by induction is a wonderful technique. A famous combinatorialist, Herbert Wilf, said induction makes you feel guilty for getting something out of nothing, and it is artificial, but it is one of the greatest ideas of civilization. It definitely guarantees that our formula is true. But another famous combinatorialist, Giancarlo Rota, noted that if we have no idea why a statement is true, we can still prove it by induction. This comment suggests that proof by induction should be our last resort and not our first. Instead, we should seek to understand why the formula is actually true. To that end, if you've encountered the sum formula before, you've likely heard about the apocryphal story of Gauss computing the sum. To do this, he supposedly relied on a result that was known at least as early as the ancient Greeks. The sum of the first n positive integers can be represented by a triangular array of 1 by 1 boxes as pictured. The array has n boxes on the bottom and on the right. If we take a second copy of the array and rotate it, we end with an n plus 1 by n array of boxes, so that there are a total of n times n plus 1 boxes. Because we use two copies of the array, we can conclude that the sum we are interested in can be found by dividing both sides of the equality by 2, resulting in the desired formula. Of course, some people refuse to believe visual reasoning as quote-unquote rigorous, so they often treat this result by taking two copies of the desired sum and reversing one copy. With the two copies, one on top of the other, then the result is obtained by adding the two sums column-wise, applying the commutative property of addition. Because each column pair in this sum sums to the quantity n plus 1, we see that the two copies of the sum of the first n positive integers give a total of n copies of n plus 1, for a total of n plus 1 times n using the distributive property. Dividing by 2 results in the formula again. Finally, some people don't like using the ellipsis notation. For those, we can use summation notation. Two copies of the sum of the first positive n integers can be written as the sum of the integers in ascending order plus the sum of the integers in descending order. Because these two sums have the same index set, we can add the sums term by term, where the i's cancel, resulting in the sum of n copies of n plus 1, which gives n times n plus 1. We have a rigorous induction proof and a rigorous algebraic proof. Shouldn't we stop there? Remember that Ross said we should think deeply of simple things. In particular, the visual proof we just saw suggests that the sum could be related to area. But do we need two copies of the triangular array? Instead, we should be able to compute the area using a single triangular array of boxes. To do this, we cut the array along this diagonal, creating one large triangle and a bunch of small 1 by 1 triangles. In particular, we have a total of n 1 by 1 triangles. The area of the large triangle is 1/2 base times the height, so 1/2 n squared. The n triangles all have an area of 1/2, and so they result in a total area of 1/2 times n. The formula pops right out from triangular areas. Anytime area creeps into the picture, a mathematician's thoughts go to integral calculus, and sure enough the formula follows from the fundamental theorem of calculus. Plot the graph of the linear function y equals x plus 1/2 and compute the area between the curve and the x-axis by determining the definite integral from 0 to n of x plus 1/2 dx. Using the fundamental theorem, we can find an antiderivative to be x squared over 2 plus x over 2, and evaluating this at n and 0 and subtracting results in n squared over 2 plus n over 2. But we can also compute the same definite integral by breaking the region up into a bunch of subintegrals. In particular, we can cut the interval 0 to n into the intervals of the form I minus 1 to I for each integer I. Then, the definite integral is the sum from I equals 1 to n of the definite integrals ranging from I minus 1 to I of x plus 1/2 dx. Again, we can apply the fundamental theorem of calculus, and when we plug in the endpoints and subtract, we get I for the subdefinite integral. This means that the definite integral of interest is given by the sum from I equals 1 to n of I. As we have computed the integral 2 different ways using properties of integrals, we get the desired formula. But do we really need to use the fundamental theorem of calculus for this computation? After all, the region in question is actually just a trapezoid, and the area of the trapezoid is given by 1/2 times the sum of the base lengths times the height, resulting in 1/2 times n plus 1 times n. Likewise, the subregions into which we divided the trapezoid are all trapezoids too. They each have a height of 1, and the average of their bases are the integers from 1 to n. This means that the area of the large trapezoid can be determined by the sum of the first n positive integers, just as we've already seen. Using only trapezoid areas, we have our result. We could call it quits now that we have 3 more area proofs, but we want to think deeply of simple things. We can revisit the notion that the sum of the first positive integers counts something, so there should be combinatorial proofs. We begin with a double counting proof, where we count one thing 2 different ways to produce an identity. In this case, we will determine the number of handshakes that occur if n plus 1 people each shake hands with every other person exactly once. We can model this handshake scenario by drawing a graph with n plus 1 nodes and an edge between every pair of nodes representing a handshake. Then the handshake question is really asking how many edges there are in this structure, which is called the complete graph on n plus 1 vertices. One way to answer this question is to first use the sum principle, going person by person. The first person shakes n hands, everyone but their own. The next person shakes n minus 1 new hands, and so on, until person n minus 1 shakes 2 new hands, and person n shakes 1 new hand. Notice that person n plus 1 has no new hands to shake and has already shaken everyone else's hand. Thus the number of handshakes is given by the sum of the first n positive integers. On the other hand, each handshake corresponds to a pair of people, or nodes in the graph, and these pairs are unordered, as handshakes are not directional. Thus the edges correspond to the subsets of size 2 people from the collection of n plus 1 people. There n plus 1 choose 2 such subsets. We have counted the number of handshakes or edges in 2 different ways, so these 2 answers must be equal. Applying the formula for the binomial coefficient n plus 1 choose 2 gives the desired formula. Double counting is excellent, but sometimes combinatorialists want a bijective proof. That is, they want a proof that shows how to create a one-to-one correspondence between 2 sets of objects. For our bijective proof, we remember that the sum of the first n positive integers corresponds to a triangular array with a base containing n dots. Now let's add a row of n plus 1 dots below this array. Then there's a map given by diagonal lines coming out of the dots. This map shows a correspondence. The first dot at the top of the array corresponds to the 2 dots in this new row that are n units apart. The 2 dots in the second row of the array correspond to the 2 pairs of dots in the n plus 1 row that are n minus 1 apart. The 3 dots in the next row correspond to the pairs of dots in the n plus 1 row that are n minus 2 apart, and so on. This continues until the n dots in the final row of the array correspond to the n pairs of dots in the n plus 1 row that are exactly 1 dot apart. This process has shown a bijection between the dots in the triangular array, with n dots in the base, and the pairs of size 2 from a collection of n plus 1 dots. This bijection shows that the sum of the first n positive integers must equal n plus 1 choose 2, which is n plus 1 times n divided by 2. Combinatorics also makes heavy use of recurrences. If we let tk be the sum of the first k positive integers, then we can consider 3 copies of a triangular array with tn dots. This gives us a total of 3 times tn dots. From each of these, we can remove a triangular array with tn minus 1 dots, leaving us with 3 lines of dots. If we put these 3 lines together, there is space for a triangular array inside with tn minus 2 dots. When we add those dots, we get a triangular array with a total of tn plus 1 dots. This means that 3 times tn minus 3 times tn minus 1 plus tn minus 2 equals tn plus 1. Therefore, the sequence tn has the characteristic equation p of x equals x cubed minus 3x squared plus 3x minus 1, which is x minus 1 cubed. Because this has a triple repeated root of x equals 1, the closed formula for tn must be given by tn equals a times 1 to the n plus b times n times 1 to the n plus c times n squared times 1 to the n, where a, b, and c are constants. We can use the first 3 values of the sequence tn to produce a linear system in 3 equations with 3 unknowns. Solving this system yields a equals 0, b equals 1/2, and c equals 1/2, so that tn equals 1/2 n plus 1/2 n squared, as we expected. Let's keep going and think even deeper about this simple fact. It turns out that the formula is a consequence of 2 powerful theorems. First up is Pick's theorem, which says that the area A of a simple polygon with vertices at integer lattice points is given by I plus b over 2 minus 1, where I and b are the number of lattice points in the interior of and on the boundary of the polygon, respectively. If we draw the integer lattice, then we can highlight the points 0, 0, 0n, and n plus 1, 0. And we can draw a triangle connecting these 3 points. The area of this triangle is 1/2 times the base, which is n plus 1, times the height, which is n. So the area is 1/2 times n plus 1 times n. But using Pick's theorem, we see that there are n plus 1 dots on the left boundary and n plus 1 extra dots on the bottom boundary. Because n and n plus 1 are 1 apart and relatively prime, there are no boundary dots on the diagonal line. This means that there are a total of 2n plus 2 dots on the boundary. Notice that the interior of the polygon is a triangular array of dots, so the number of interior dots is the sum of the first n minus 1 positive integers. Applying Pick's theorem, we get the area to be the sum of the first n minus 1 positive integers plus the quantity 2n plus 2 divided by 2 minus 1. But 2n plus 2 divided by 2 is n plus 1, and the positive and negative 1 cancel, and we are left with the fact that the area equals the sum of the first n positive integers. Therefore, we get the formula that we wanted as a consequence of this very powerful theorem called Pick's theorem. More importantly, we see that Pick's theorem is the connector between area proofs and combinatorial proofs. Pick's theorem turns out to be equivalent to Euler's polyhedral formula, so it isn't surprising that we can use Euler's theorem about planar graphs to prove the formula we want. Euler's theorem says that if we have a planar graph with v vertices and e edges, and the graph divides the plane into f faces, then we must have v minus e plus f equal to 2. In this theorem, a planar graph is a collection of vertices and edges where none of the edges cross each other. With Euler's theorem in hand, we can draw this graph consisting of a triangular array of triangles. We note that the vertices in this graph form a triangular array, and we assume that the number of such vertices is given by the sum of the first n plus 1 positive integers. If this is the case, then this diagram also encloses a total of n squared triangles. There is also a face outside the diagram, so there are a total of n squared plus 1 faces. Finally, we have 3 types of edges, And if we group those types together like this, we see that the edges form 3 different triangular arrays, each corresponding to the sum of the first n positive integers. Therefore, the number of edges is 3 times the sum of the first n positive integers. Applying Euler's theorem, we see that 2 is equal to the number of vertices minus the number of edges plus the number of faces. We can move the n plus 1 to the end and group together the sums of the first n positive integers. Then, the 2's on either side of the equation cancel, and we can add the negative 2 times the sum of the integers to the left. Finally, dividing by 2 results in the desired formula. Euler's theorem is quite a powerful theorem, but it is fun to see it give the expected simple formula here. Of course, we still aren't finished, because we can get more if we continue thinking deeply about this simple formula. In particular, we can also encounter 2 physical proofs. For the first one, consider a water flow diagram where there's a source S and a terminus T, connected by a series of aqueducts. The source is connected to n pipes, each of which feeds into 2 pipes at a junction. Then, pairs of pipes feed back into one of n pipes, which in turn feed into the terminal point. We label each of the aqueducts with the rate at which the water flows. The first pipes have rates n plus 1 each. The intermediate pipes split into pairs that add to n plus 1 as labeled, and the ending pipes have rates given by the first n even integers. Because the incoming and outgoing rates are the same at each juncture point along the way, the total input at t must equal the total output from S. If we run this for 1 minute, there are a total of n times n plus 1 gallons output at S, and a total of the sum of the first n even integers input at t. From this, we get the desired formula for the sum of the first n integers after we divide by 2. And for our final proof, we utilize the physics of centers of mass. Imagine a platform with the distances marked off at the first positive n integers. Place a weight of mass 1 at each integer coordinate. If we want to balance this platform on a fulcrum, we have to find the center of mass. It turns out that in this case, the platform will balance when the fulcrum is precisely in the middle of the platform. We can convince ourselves of this because if there are only weights at position 1 and n, then the platform balances at the midpoint of the 2 x-coordinates, which is n plus 1 over 2. But then the remaining weights of mass 1 pair up with equal weights at equal distances from the fulcrum. If n is odd, there is one final weight that sits directly on the fulcrum. Adding these pairs does not affect the center of mass. On the other hand, we can compute the x-coordinate of the center of mass as the sum of the moments of mass divided by the total mass of the system. A moment of mass is given by the product of the mass and the distance given by the x-coordinate. Plugging in the mass of 1 for all masses and the positive integers for the corresponding x-coordinates, we get this equality. Multiplying both sides by n once again yields the formula for the sum of the first n positive integers. It's really amazing what thinking deeply about simple things can do for you. In this case, we found 12 proofs for the sum of the integers formula that exposed us to a variety of mathematical topics. We begin with the tried and true induction proof, along with the classic visual proof, reflecting the reverse and add procedure. But we didn't stop there. We considered area-based proofs using the area formulas for triangles and trapezoids, and even invoked the fundamental theorem of calculus to compute an appropriate definite integral. We saw 3 combinatorial proof techniques using double counting, constructing a bijection, and using linear recurrence relations, along with a little bit of linear algebra. We learned about 2 heavy-hitter deep theorems, showing how to use Pick's theorem and Euler's theorem to get the result. And finally, we investigated how to use physical ideas, namely water flow diagrams and centers of mass, to obtain the desired formula. Now it's your turn. Keep thinking deeply about this simple formula. What other proofs can you find that reveal interesting mathematical ideas? This video is based on a recent expository collection of 32 proofs of the formula, written by Tom Edgar and Enrique Trevino. The description contains a link to that paper, as well as many other sources that informed this video. Which proof was your favorite? Comment below, and if you liked this video, consider liking, subscribing, and sharing with others.